students, welcome to Sunil's tutorial. I'm Sunil Midwani and today we'll be doing this chapter called as Control and Coordination. Let's see the mechanism of hearing today. Right, let's try to understand the mechanism of hearing. Now, once sound waves are generated, how do the sound waves move and how is it that you are able to actually hear this, right? Now, the sound waves from the external environment are perceived by the pinna, right? External pinna and are transmitted to the, I don't think it's shown here. We had discussed this in the previous lecture. Wait, I'll just show it to you. Sound waves from the external environment are perceived by the external pinna and are transmitted to fenestra vestibule. Fenestra vestibule. Right? Now I presume we had seen this in the previous lecture, the fenestra vestibule. The oval opening window, right? The window that is just behind the tympanic membrane, the oval opening, right? That's my fenestra vestibule. We had seen this in the previous lecture. It is there in the middle here, and the three ear ossicles have an opening window, and which is called as the fenestra vestibule, right? So sound waves from the external pinna are transmitted through the auditory canal and reach the fenestra vestibule, right? Once they reach there, then fenestra vestibule through the eardrum and the auditory ossicles. Through the eardrum and ear ossicles. Fine. Now, what do the auditory vesicles do? The auditory vesicles, they amplify the sound vibrations. The auditory vesicles amplify the sound vibrations auditory vesicles amplify the sound vibrations and the eustachian tube serves to equalize the pressure on the sides of the tympanic membrane. So you have sound waves that will go from the external ear through the auditory canal, through the eardrum, through the ear ossicles and would reach the fenestra vestibule. You also have the auditory vesicles that would amplify the sound. The eustachian tube would make sure that you have equal pressure on either side of the auditory tympanic membrane, that's the eardrum, right? Now, the fenestra vestibule relays the sound vibrations to the two fluids of the ear. Which are the two fluids of the ear? We have two fluids in the ear. One is called as the perilymph and the other is called as the endolymph. So what does the fenestra vestibule do? It relays the sound vibrations to the perilymph. The fenestra vestibule. Now the fenestra vestibule, relays the sound vibrations to the perilymph of the vestibule. Right, and subsequently it will relay the vibrations to the perilymph of the vestibule and subsequently to the scala vestibule. Okay, so you would have the sound waves that would be transmitted from the fenestra vestibule and it would go into the perilymph, and from the perilymph they would go into the scala vestibule. Scala vestibule, we have this diagram here of scala vestibule. Here's your scala vestibule, right? So you would have, guys, let's see this. From the external ear, auditory canal, eardrum, ear ossicles, fenestra vestibule, from fenestra vestibule into the perilymph, from perilymph into the scala vestibule. That's your entire path of sound. Fine, do we get this in clear? Now from scala vestibule, the vibrations are passed vibrations are passed to the apex of cocella and to the scala tympani. And then transfers the whole length of cocella and then transfers the whole length of cocella. Right? Once they reach scala vestibule, then they are passed to the apex of the cocella. From scala vestibule, they go to the apex of the cocella and they transfer the whole length of the cocella, right? That's the entire passage of sound, right? So in this way, by transversing the whole length, you would have the sound waves that would reach, in this way the vibrations are set up in the perilymph because they pass through the perilymph and they go into the basilar membrane. Here's your basilar membrane, right? They would reach the basilar membrane. Let's take this down. In this way, vibrations are set up in the perilymph vibrations are set up in the perilymph and pass to the spinal coil spirally coiled basilar membrane. They pass to the spirally coiled basilar membrane in the endolymph of scala media. So from perilymph they go into the endolymph, which is present in scala media, which should again be shown to you there in the diagram. Right now, the basilar membrane carries a row of sensory hair cells. The basilar membrane carries a row of sensory hair cells. Carries a row of sensory hair cells called the organ of Corti. Right? No. Huh? Yes, fine. Organ of Corti. Now these hairs of organ of Corti, these hairs of organ of Corti are sensitive to sound vibration. Are sensitive to sound vibration. The hair which is present in the organ of Corti are sensitive to sound vibration. When sound vibrations move the basilar membrane up and down, when sound vibrations move the basilar membrane up and down, it distorts the hair cells of the organ of Corti. It distorts the hair cells of organ of Corti. It distorts the hair cells of organ of Corti and results in the generation of nerve impulse, and results in the generation of nerve impulse, results in the generation of nerve impulse for production of sound. That's how your impulse for production of the sound is produced, right? So you would have from pinna to the auditory canal, from the auditory canal to the tympanic membrane, from the tympanic membrane you would have the 3 ear ossicles, from the 3 ear ossicles you would have to the fenestra vestibule, from the fenestra vestibule, once it reaches fenestra vestibule, it would go into the perilymph. The vibrations would be transmitted to the perilymph, and from the perilymph they would go into the scala vestibule, right? From the scala vestibule they would be passed to the apex, would pass the entire length of the cocella, and that way you would have the vibrations that would be set up in the basilar membrane of the endolymph, right? Now the basilar membrane has hair, extremely sensitive hair, which is called as the organ of Corti. As the basilar membrane moves up and down, these hair are disturbed, and this disturbance in the movement of the hair produces the nerve impulse which produces the sound. So that's how the nerve impulse for production of the sound is done, right? The auditory nerves that branches over the vestibular apparatus and cocella carry carries the impulse to the auditory area of the brain. Area of the brain. Right? The human ear is able to perceive its pitch, is able to perceive its pitch from 16 to 20,000 cycles per second. Right, that's the minimum and maximum frequency that can be heard. Right, so let's just go through this once again. You would have sound waves collected by the external pinna would pass through the auditory canal, eardrum, ear ossicles. Then you have, this is your oval window, that is your fenestra vestibule. Once it reaches fenestra vestibule, then the impulse would be transmitted to the perilymph. Right, from the perilymph it would go into the scala vestibule. Once it reaches the scala vestibule, then it would go to the apex of the coccyla, would transverse the entire length of the coccyla. Right, from there it would reach, that would transmit the vibrations to the perilymph, right, which is coiled in the basilar membrane. Right, now the basilar membrane also has hair-like structures, right, which are called as the organ of Corti. Now, as the vibrations are transmitted to the basilar membrane, as the basilar membrane moves up and down, the hair which is there in the basilar membrane would have certain vibrations, right? Their equilibrium would be disturbed. Now, these vibrations would then set up nerve impulses, and these nerve impulses then would be carried to the auditory area. That's how hearing is done, right? Now, another important function of the ear is it acts as an organ of balancing. Ear acts as an organ of balancing. Right, what would the ear do? It would make sure that your head remains straight. Now, how is it that the ear is able to do that? Right? Let's try to understand how is it that the ear is able to make sure that your head remains straight. Right? Now, the vestibular and the semicircular canals act as the organ of balancing. The vestibular and semicircular canals act as the organ of balancing. These are the two organs that make sure that your head remains straight. Now, let's see how does this happen. The semicircular canals are 3 in number, and each canal, we have done the structure of the human ear, in which we've said that the semicircular canals are 3 in number, and each canal at its lower end is enlarged, and each canal at its, this is your structure that we had seen previously, each canal at its lower end is enlarged and forms, lower end is enlarged and forms the ampulla. Right? We've seen this when we are doing the structure of the ear, that you would have each the three semicircular canals. The lower end of each is amplified and that end is called as ampulla. The ampulla then carries a sensory spot which is called as the cristae. I can say that the ampulla carries a sensory spot called cristae for maintaining equilibrium. Fine, do we get this in here? Now, we had seen that you have the vestibular apparatus consists of the semicircular canals. It also has the utriculus and the sacculus, right? Now, I can say that the canals open into the utricles. The canals open into the utricle. First, I'm giving you the structure, and then I'll show you how this structure helps in maintaining the balance of the head. Utricle, by both the ends, the canals open into the utricle by both the ends. Right? Now let's actually come to how the balancing act is done. This is the structure that we have. We have the semicircular canals which have ampulla. Ampulla have cristae, and the canals open into the utricle. Both the ends of the canal, the swollen end and the non-swollen end, are in the utricles. Right? Let's see this. Now when the head tilts, the endolymph of the semicircular canal does not move as fast as the head. The endolymph of the semicircular canal does not move as fast as the head. Right? But the sensory hair of the cristae move through the endolymph, they move through the endolymph and stimulate the sensory cells. That's your organ of body, right? So as the head would tilt, the endolymph would, which is present in the semicircular canal, does not move as fast, but the sensory hair of the cristae would move through and they would stimulate the sensory cell. Now, the sensory cells sets the nerve impulse, and we know that as soon as the sensory cells are moved, there would be an impulse that would be created. So what would happen is that the sensory cells, we just saw this in the mechanism of hearing. As soon as the sensory cells move, which are present in the basilar membrane, you would have a nerve impulse that would be generated. So the sensory cells sets the nerve impulse which is fired off by the auditory nerve. Sensory cells sets the nerve impulse which are fired off which are fired off by the auditory nerves. Right? Now, the auditory nerves then convey the stimulation to the brain. As soon as the head moves, since the endolymph has not moved and your basilar membrane has moved, the organ of Corti would send an impulse to the brain, and the brain would come to know that the head has been tilted, right? So you would say that the auditory nerves then convey, the auditory nerves then convey the stimulation to the brain, the stimulation to the brain would convey the stimulation to the brain, and a set of reflexes. The brain would know that there is no auditory signal here, but it is a signal that the head is tilted. So hence reflex message would be sent, and set of reflex, it would set off a reflex tending to return the body to its normal balance. Tending to return the body to its normal balance. Right? So the cristae of the ampullae help in maintaining the dynamic equilibrium of the body. Cristae of the ampullae. The cristae of the ampullae help in maintaining the dynamic balance of the body. Right? Now, the vestibule contains two sensory spots. One, you can say that the vestibule contains two sensory spots. The vestibule contains two sensory spots. One is the macula of utricle, and second is the macula of sacculus. These are the two sensory spots, and the vestibule contains these two sensory spots, and they help in maintaining the static equilibrium and the static acceleration of the body. These sensory spots help in maintaining static equilibrium and static acceleration of the body. So when the body is in motion, it is your ampullae, that the cristae of the ampullae that help in maintaining the equilibrium. When the body is at rest, it is the macula of the utricle and the macula of the sacculus that help in maintaining the equilibrium of the body. Thus, here not only does the auditory function, but also helps to maintain balance of the body. Right? Right. We'll stop this here for the day. Thank you very much.